Okay, so we're going to look at the trig graphs. So we're going to start with kind of the basic trig graphs and kind of going over what they all look like and that sort of thing. And then we'll do maybe another video then looking at the kind of transformations and the related trig graphs. But we're just going to go through kind of from the notes here, just because it's kind of laid out in kind of a straightforward enough way for us to go through them all. And then we'll kind of see after that. So for looking at our trig graphs, there's a few keywords that we need to be kind of aware of and be fairly familiar with. The period of the graph is the horizontal length of one complete cycle. So it's how long on the x-axis it takes for your graph to go through one complete cycle. Because all of our trig graphs follow a kind of a cyclical pattern, if you like. They're all repeating graphs. So we can kind of get used to what one cycle looks like, and then that helps us kind of determine the period of the graph, like how long it's going to take for it to complete one cycle. So when we talk about that, how long does it take, we're talking about in terms of the x-axis. How long in terms of x points will it take until I reach an x value that gives me a value that I've kind of already had, essentially. The range of the function is the interval between the maximum and the minimum value, so the lowest y value to the highest y value. So again, fairly straightforward. But the range, again, just remembering that it is an interval. So we write it using our brackets, and we're essentially summarizing, what is the range of y values that this graph hits? Okay, so where does it go from the smallest to the highest point? What are all the points that I'm going to get out? The amplitude is the distance from what we call the midline to the highest or the lowest point. Now, midline comes after that. Midline is the line halfway between the highest and the lowest points of the graph, and the amplitude then is the distance from that line up to the highest point and down to the lowest point. Okay, so they kind of go hand in hand there. So those are kind of the key points that we need to think about when we're looking at these graphs. So looking first of all at the sine graph, this is an example of what it looks like. And thinking about what we said there about a cycle, one cycle of your sine graph is like this here, what I'm kind of highlighting in yellow here. So that is one cycle of your sine graph. So if you're trying to spot a graph and you're given a cycle, you need to get familiar with what kind of the cycle looks like for the different graphs. So a sine graph starts at essentially 0, 0, but really more kind of generally, if we like, because we will be looking at the general ones, it starts at the midline. Okay, so for your standard sine graph, your midline will be 0, will be the y-axis there. But starts at the midline, goes to the maximum, goes to the minimum, and then back up to where it started. So each of these graphs has to kind of hit that max, min, and back to where it started. So the period of the graph is 2 pi, or 360 degrees, and that's the green part here. So that's the length of time on the x-axis that it takes for us to get through one full cycle. So we can see that takes right up to 2 pi, or 360 degrees. The amplitude then is the distance from this line, the middle line, up to my highest point, which is up here. So my highest point, the distance there, is just 1. So for our standard sine graph, the amplitude is just 1. The range we said was the kind of range of y values that we hit. So we can see there that we're hitting the point 0, 0, we're hitting the highest point we're going to is 1, the lowest y value we go to is -1, and we're kind of hitting every y value in between then. So our range we represent by this here as -1 plus 1, and using the square brackets just shows us that both of those points are included in the range there. The amplitude we've said is 1, and our x is equal to 0, y is equal to 0 as well. And then domain, we should remember, is the x values. So the domain is the x values, and the sine graph is defined for every x value from -infinity to +infinity. So this graph will continue following that same pattern forever in both directions. Looking at cosine, we see something similar again. So if I highlight again one cycle in the yellow highlighter here, we can see that the cycle looks slightly different. It's more of just kind of a U shape nearly. So the cycle looks slightly different, so that makes it a little easier to differentiate from your sine graph. Again, amplitude, the distance from the midline to the highest point, is still just 1. Okay, the period here again is still just 2 pi. So it takes me until I get to 2 pi for the cycle to be completed. The range is -1:1, the domain is the same, and at x is equal to 0, y is at 1, which is my highest point. Okay, so what we're seeing here, in the last one we saw the sine graph. When x was equal to 0, it was at that midline. When x is equal to 0, the cosine graph is at its maximum point. Okay. Then continuing on looking at tan, we can see that tan is the first of these graphs that looks different from the previous two. So instead of us having a kind of continuous curve, tan has a very particular shape, and that shape then just repeats. So one cycle of the tan graph looks like that there really, and the period this time is actually pi. So instead of being 2 pi, it's actually just pi, or 180 degrees. The domain again, still minus infinity to plus infinity. The range is all real numbers, so we can see that from this graph we don't have a highest point or a lowest point. That graph continues on forever. What we do have are what we call asymptotes. And an asymptote is a point that your graph doesn't touch. Okay, and we have asymptotes here at 3 pi over 2, and we have an asymptote here at pi over 2, and we've another asymptote here at minus pi over 2. And asymptotes are points where your graph is never going to touch. And how we've represented that in terms of the key points here that I've laid out is this part here, undefined. Okay, our tan graph is undefined at certain points. So it just has no value at those points. And what those points represent is actually all kind of multiples of pi over 2, or 90 degrees. It comes from our unit circle. So if you look back at your unit circle video, when we were looking at how that's related to our trig ratios, we said that for any point here, this line is my opposite and this line is my adjacent. But if I look at 90 degrees, so up here, so if I'm up here, my opposite value, we could say, is still just 1, but my adjacent value would be 0. So tan would be 1 over 0. Okay, so 1 over 0. And I can't divide something into 0 parts. Okay, so I just get an error. If I try to do that on my calculator, I just get an error. So that's where it comes from. That's why it's undefined. But more generally, if we just kind of remember from the shape of it, it repeats after pi, and it has those points where it has no value, all those multiples of 90, or pi over 2. So looking at how we kind of use all that information, we're looking to sketch a graph of y is equal to sine x in the domain minus 360 is less than or equal to x is less than or equal to plus 360. So let's have a look. So if we draw kind of some axes for ourselves here, just, oh gosh, it's gone crazy. There we go. So we'll kind of get that sorted a bit more there, and maybe we'll try and do it with the line across. Well, that's not the worst. No, oh no. Okay, I think we're gonna have to forget about that one. So we're just gonna have to draw it across and say nothing. Okay, so let's have a look. So our sine graph. So how we're gonna sketch it? So we could sketch our graph by plugging in different values. Generally, kind of, again, those multiples of 90 will give you those whole number values that you can work with. But we should have some idea at this point of what the behavior of our graph is at these certain values. So we're just going to kind of take a sketch approach to it here. So 360, and we go the same for our side. So 90, 180, 270, and 360. Okay, so let's have a look. So at 90 degrees, my sine graph would be at the highest point here, which is 1. And when it gets to minus 1 is when it hits 270. Okay, same thing applies over here now, kind of in the opposite sense, that when we're at these points here, and at multiples of 180, I am along the y-axis there. So then starting from 0, 0, we know that it starts here, it goes up to 90 degrees, it goes up to 1, then goes down through 180, down to where we have 270, and back up then to my 360. And the opposite side obviously is just kind of going in a little bit of an opposite way. And again, just sketching that as best we can. Okay, so just to give us some sense of what we're looking at. So we're looking to see how many solutions there are to y is equal to a half. So let's kind of plug that one in, and drawing a little bit of a sketch across for ourselves. And just we're going to see where it interacts with our curve. Now we're not actually asked to find what those values are, just how many. So we can see that there are 4 points where it intersects with our graph. So there are 4 solutions to sine x is equal to a half. Okay, so we can see we can sub these into our formula, or we can just simply kind of draw a sketch of it as it is. And the same thing goes for cosine. If we had to sketch cosine, we could kind of make a fairly good stab at it in that sense. But you can sub them into your calculator to get those values. But really, it's those 90-degree values that are going to give you the good amounts that you can work with, and more than other ones really. If we look at then reflections of sine and cosine. So we've seen the graph of sine and the graph of cosine. The graphs of minus sine and minus cosine are the same as the standard ones, but reflected in the x-axis. So if we look at this diagram here, the dotted line is our usual sine graph, and we can see that our minus sine graph is the opposite way around. It's flipped around completely. So it's what we call inverted in the x-axis. So starting at 0, 0 goes down instead of going up. That's just a complete kind of mirror reflection. We get the same thing with cosine then. We had said that cosine at the x-axis starts at the maximum point, but we can see that minus cosine starts at the minimum point. Okay, so that's one good way of recognizing whether it's a standard one or whether it's a minus sine or a minus cosine, because the minus cosine starts at the minimum point, and minus sine, we can see that the first point that it goes to after the origin is the minimum point. Okay, so kind of thinking that minus those minimum values. And that's kind of the best way for us to see whether it's the standard sine or whether it's the kind of reflection. So the orientation is what we would call that. So we'd say that the graph is positively or negatively oriented. So if it's positively oriented, it's your standard sine or cosine. If it's negatively oriented, it's your reflection. It's your minus sine or minus cosine. So that's kind of the general forms of these graphs. We're going to look at in the next video is more about the different parts, the period, the domain, or the period, the range, the amplitude, those sort of things, how we can transform those and applying that then to exam questions, because that's really more the sort of thing we would see rather than the kind of standard graphs.